All right, welcome to an overview of geometric distributions. All of this material deals with contents of section 8.2, and it would be a good idea to have your book available because I'm going to be referring to two specific problems and also formulas on some particular pages, and I'm going to want you to kind of go along with me. So pause the video if you need it and get all those items ready. If you were in class, then you participated in activity 8B, which is actually found on page 539 in your book. If you weren't here, you should try that activity first. We focused on questions 2, 3, and 4 in that activity, and what we found out is that there are three probabilities there that are all pretty straightforward to calculate. When you're trying to find the probability that Mrs. Hathaway assigns exactly 10 homework problems, remember that that probability would mean that there were 9 wrong guesses followed by 1 correct guess. And so we could calculate that probability by simply taking 6/7 to the 9th, representing the 9 failures, times 1/7, representing the 1 success, and that would give us a probability that's somewhere in the neighborhood of 0.035, and that is the probability of the correct guess on guess number 10. And that was number 2. Number 3 was found by trying to get the probability that the correct guess happens before number 10. That's a little more complicated because we have to think about it happening on the first guess or the second guess or the third guess, but there is a pattern that evolves here, and here's what it looks like. If we're correct on the first guess, that would be a 1/7 probability. If it happens on the second guess, well, that would mean we're wrong the first guess, so we have a failure followed by a success. Or we could have 2 failures followed by a success. That would be correct on the third guess. And there's a pattern that evolves here, and the last term in that pattern would be 6/7 to the 8th, or 8 failures, followed by the success on the 9th. This whole thing, if you evaluate it, turns out to be a 0.75. Okay? And we'll find out later you can use the geometric CDF command to do the same calculation. We also found out in class that for number 4, we could find the probability that you assign more than 10, meaning that you guess incorrectly at least 10 times or possibly more, by simply calculating the probability that you get your correct guess after 10 by the following. Oops, after 10 is what I should say. And that's going to be simply 6/7 to the 10th power. And it turns out this is the same as 0.214. If I add all these probabilities together, I get something awfully close to 1. What we discovered in using all this is that basically this problem illustrates all of the formulas that we're going to be using in this section. And so the formulas may look a little scary, but they're really not that bad. The first page in your book I'd like you to find is page 540. That has the conditions for the geometric setting. Please notice that the first 3 of those are exactly the same as the binomial setting. The only one that's missing is that we don't have a fixed number of observations n. That's replaced by condition 4, which says the variable of interest is the number of trials required to obtain the first success. We have a success, we stop. And up until we have a success, we're assuming that we have failures. So it's actually a simpler setting in that particular case. On page 541, we have a formula that's very similar to what we used to solve number 2, because in that particular case, we're saying if n is any one of the values mentioned above, the probability that the first success occurs on the nth trial, say at 10, is simply found by taking n minus 1 failures times the 1 success, and that's going to give us the probability that we want. If you continue to turn pages, actually, let's go back to that formula for just a minute. I want to show you the geometric PDF command. This particular command here, or this formula, would be similar to what you would get from the geometric PDF. So if you're trying to do this calculation on paper, geometric PDF is going to give you the same outcome. And what you're going to type in is P, comma, and it's going to be N. Okay? So for example, from the problem we just did a minute ago with Mrs. Hathaway's class, we could type in geometric PDF of 1/7, comma, 10, and we're going to get that familiar 0.035 that we saw before. Okay, let's continue onward talking about the formula that you're going to find on page 545, the mean and standard deviation of a geometric random variable. Those particular formulas we're going to be using shortly in the context of an example. So if you want to write those in your notes, that would be a good idea. On page 546, there's one last problem or one last formula, and that one ties directly to number 4 from Mrs. Hathaway's class example, because it tells you that if you want to find the probability that it takes more than a set number of trials to see the first success, that you simply have to take that N and raise your probability of failure to that particular exponent, and you're going to get the probability that you're looking for, just like we did in that fourth problem. At this point, what I'd like to do is work through two problems with you. They're found on page 550. The first one is problem 48, and it's called Language Skills. So if you would take a minute and read that question, and then turn the video back on when you're ready. So we're back. We're here with problem 48, and this is found on page 550, excuse me. And in part A, as you know, we are looking to count how many individuals can they expect to interview in order to find one who is fluent in Farsi. Anytime I hear that word expect, it makes me think about using the mean, because if you remember in these distributions, the mean is the expected value. So the formula that we're going to be using in this particular case is found back on one of the previous pages. It looks like this. Mu in this case is real simple. It's basically 1 divided by P. And in this particular case, P is given to be 4%, because 4% of the applicant pool is fluent in the language that they're looking for, which is Farsi. So I could take 1 and divide it by 0.04. When I do that, I'm going to get 25. So the expected number of interviews is actually going to be 25. They would have to interview 25 people before they could reasonably expect to find someone who's fluent in Farsi. Of interviews is 25. Now understand, this doesn't mean that they're guaranteed to have a fluent Farsi speaker in 25 interviews. It doesn't mean they wouldn't need more or maybe even get lucky on the first interview. It just means that it's reasonable to expect it would take about 25. So if they were gathering candidates for these interviews, they want to make sure they had at least that many. In part B of the same question, it says, what is the probability they'll have to interview more than 25 or more than 40? Well, this is where we can start using that very last formula that we had and say the probability that X is greater than 25, well, that would mean that they have 25 failures. So we're going to take 1 minus 0.04 and raise that to the 25th power. That seems awfully simple, and it is. What we're going to get here is 0.36. So the probability that they're going to go more than 25 interviews is still pretty significant, but that just gets you an idea of how big that is. The probability that they'd have to go more than 40 is done in the same way, only this time the exponent we use is going to be 40, and that's going to give us a probability of about 0.20. So they have about a 1 out of 5 chance of having to go 40 or more interviews. That's a good thing to know if you're setting up those particular interviews or trying to gather a pool of applicants. That's problem 48. Last but not least, we have problem 49 on that same page, and it's about shooting free throws. So take a minute and read that question, and then come back when you're ready. In the first part of this question, we're being asked what we have to assume to make this a geometric model. So there's a couple of things. We have to assume the shots are independent of each other. We have to assume the probability of success is the same for each shot. We also have to assume that a success is actually missing a shot, which might seem weird. So the probability of success is going to be 0.2. So those are the things we'd have to be assuming in order to make this a geometric setting, because they just fit with the conditions. Now let's do some calculations with that. Part B says, what is the probability that the player will make 5 shots before she misses? Well, that almost kind of tells us how to set this up. So we want the probability that she makes 5 shots and misses on the 6th one. So x, our x variable that we're counting here, is going to equal 6, because that's the first time that we have a success, even though a success in this case is missing. So we're going to take there to be 5 failures, and the probability of success is 0.2, so the probability of failure is 1 minus 0.2, or 0.8. That's got to happen 5 times, multiplied by 0.2 being the success on that last shot. When we multiply that out, we're going to get 0.0655. And that's going to represent the probability that she makes 5 in a row and misses on the 6th. Okay? Last part, part C. The probability she makes at most 5 shots before she misses. So in that particular case, we're saying it's just a tiny bit different. We're trying to find the probability that x is less than or equal to 6. So she may make 5 shots or she may make less, because that's what that at most tells us to do. Well, that would be the same thing as the probability of x being greater than 6 subtracted from 1. This is a place where we can use our complement rule. Take a minute to look at that if you need to just wrap your head around what we're doing. But instead of having to calculate all those pieces, what we could do is calculate something simpler. In this case, 1 minus the probability of failure to the 6th power, because that's something that we can calculate much more simply. That's going to be 0.8 to the 6th power, and that's going to be a 0.7379. The last thing that you could consider to do this if you were working on your calculator is you could also make use of the geometric CDF command here. And what you'd run it with in this case is you would put a 0.2 for your probability of success and a 6, because what the calculator is going to assume is that you want the probability of exactly what's stated in our inequality up here. Okay, so this statement is exactly what you're looking for with this geometric CDF command. So having a success on the 6th trial or any time before that, which is kind of what the question's asking for, it gives this exact same value. So as you're working on that, you might try checking your answers, but this is how you might do it algebraically if you couldn't use the geometric CDF command, or it's just another way to approach the problem. All right, that's it. Thanks.